Hi, I'm David Nola, and I'm going to talk about convolutions and how we build on these to create convolutional neural networks. So, starting off with our motivating example here, what we want to explain is this fundamental building block, the convolution operation. And so, what we can see we have here are our source pixels coming in from our source image. We have this convolutional kernel or filter that's applied to that source image, and the result of this operation is essentially a new output image, you could say, or activation map, as we call it. Now, what I think really helps to better understand this is to actually start in the 1D case. So, taking our source pixels, our kernel, and our destination pixels from the previous image, we're just going to flatten these out and look at one dimension. What I'm going to do first is rewrite what we have here a little bit. So, we're going to take these source pixels and we're going to call these our inputs now. And we're going to take our destination pixels and call that an activation map. But the important thing here is that we have these kernels. And it turns out that kernels work just like weights in a dense neural network. So each of these kernels at every input step is simply a weighted sum over the input space it's connected to. So let's put some numbers to this and see how it's actually applied. So we're going to assign a few weights to this kernel. So we're going to have a 0 weight, a positive weight, and a negative weight to this kernel. And pay attention to these color codes because they're important. And we're going to see at this first step, those just sum out to 0. So nothing's happened here. But when it starts to get interesting is this second step. So we can see that we've transitioned from a positive set of inputs into a negative input, and now this kernel has detected something. So what we're doing here is we're taking these weights and applying them in a sliding fashion across our window. And it's important to note that these weights are shared. So you can see as we've moved between these two steps, we're using the exact same set of weights. So this is our kernel, and it stays fixed as we slide it across this window. So we'll do this a few more times. And you'll notice that in two instances of our input, we've switched from positive to negative. And this convolution operation, or sliding kernel approach, has detected both of these transitions. So what do we have here? This is an example of a single 1D convolution being applied with a single kernel. So what this kernel does is detects shifts from positive to negative. So it's essentially an edge detector. And this is really cool because essentially we have an equivalency here between kernels and detectors. A kernel is a detector. So now let's take this and apply it to the 2D case and see what we do then. And it turns out that what we have is pretty much the same thing. So we can see this yellow region with the weights in the bottom right is our kernel, and we just slide it across the entire 2D space, just the same way we did in the 1D case. Now, so what does the actual output of these look like, on a real-world image? So what we're going to do is take a very similar kernel to what we had before. We're going to put a negative one next to a positive one, and we're going to slide it over this entire input image. And we had an edge detector before in the 1D case, and it turns out we get the same thing in the 2D case. And this is really cool because this is basically the simplest kernel that we could possibly come up with, and it's done something extremely powerful. It's picked out all of the vertical edges in this image. So great, we have this convolution operation, and we've seen how powerful even very simple convolutions can be. And they're based on these kernels, which are just weighted sums essentially, slid over an input space. So what can we do with these? So we can create neural networks out of them, it turns out. So these neural networks are called convolutional neural networks. And what they are a bunch of stacked convolutions with a bunch of kernels used in each layer. And those kernel weights are going to be learned by backpropagation. So what this looks like in an actual architectural format is something like this. So we have an image. You slide kernel over it to get an output layer, and then that gives you an output image. And then over that, you slide a separate set of kernels, and those give you another set of output images. And you just repeat this process over and over and over again. Now, why do we want to make networks deep like this? We've seen that, a single convolutional kernel is quite powerful, so why do we need to stack them like this? So we're going to start by looking at something called deconvolutions, which basically just show you what a network is seeing. So we're going to look at basically what AlexNet's learned. So based on these input images up at top, they just look like a bunch of edges. These are just cropped out of ImageNet. You can see that what AlexNet sees are essentially the edges of the image. And this is what's happening on our very first layer. So that's cool. That's the result we've arrived at so far. But what happens when we stack these? So we can see at our second layer, we're starting to see more complex shapes. The things that the network picks out are more complicated. So I think my favorite example is probably the one in the bottom right here. You can see that the network is looking at these corners. And when you think about it, a corner is really just a combination of two edge detectors. But we can even do things like get round shapes by combining multiple edge detectors at different orientations. And essentially what we're doing here is we're building on our simple edge detectors and making more complex detectors out of them. And this trend continues as we go deeper into the network. We get higher and higher level representations. So now when we move to the third layer, we're not just looking at corners or round shapes anymore. We're looking at entire textures or even primitive objects like the leg of a person. So as we go deeper and deeper, these detectors are building on one another, combining together, and creating higher level concepts. And this is the fundamental principle that makes convolutional neural networks so powerful. You build on simple concepts to create complicated ones deeper and deeper into the network. By about layer 5 or so of AlexNet, you get detectors that are detecting entire objects, like an entire dog. So empirically, we know that convolutional neural networks perform very well on many image tasks. This is what they're most famous for. But I actually want to conclude with some myth busting regarding convolutional neural networks. These are things that I think have been ingrained in what we believe about convolutional neural networks since they became popular in about 2012. And I just want to address some of these issues because I think it really expands the range of applications in which convolutional neural networks are relevant. So the first myth that I think is important to address is the myth that convolutional neural networks only work with big data. But it turns out that this actually isn't the case. The state of the art for one-shot learning is actually accomplished with convolutional neural networks, specifically Siamese and non-parametric convolutional neural networks. And what one-shot learning is it's just learning where you have only one example in every class. So you'd have one picture of a cat, one picture of a dog. Your goal, build a dog versus cat detector. So even with those two images in your data set, the state of the art is still held by convolutional neural networks in many cases. The second myth I'd like to address is that convolutional neural networks only work for images. Now, I addressed this a little bit when I talked about 1D convolutional neural networks that are often applied to time series data. This can include speech, but it also extends to things like text or even predictive diagnosis using electronic health records. And even in the 2D case, voice and speech tasks have been solved successfully using convolutional neural networks. So there are actually a wide variety of domains in which convolutional neural networks are appropriate. And the last myth, and maybe one of the most prevalent ones, is that neural networks are all black boxes. And honestly, this used to be true. Today, they're a lot more like gray boxes, and they're becoming more and more white by the day as research continues. So we are getting better and better at understanding what neural networks have learned. So those images I was showing you on the previous slides, where we're looking at what the network is paying attention to, this is done using something called a deconv net. So this approach lets us probe into a network and actually see what it's learned visually. And so tools such as these have been developed over time, and they make interpreting what convolutional neural networks have learned a whole lot easier. So these convolutional neural networks really aren't so black boxy anymore. We can actually understand them. So that concludes my explanation of convolutional neural networks. They're great in practice. They work in many domains, and I hope you have a lot of fun going out and finding ways to apply this and do interesting things with them. Thank you.